Consider this absolute, unshakable fact. Despite every handshake you've ever given, every solid surface you have ever leaned against, every texture your fingertips have ever explored, you have never, not once, truly touched a single thing in your entire life. Not the phone or keyboard you are using right now, not the ground beneath your feet, not the fabric of your clothes. This isn't a riddle or a philosophical sleight of hand. It is a fundamental, unyielding law of the universe, written in the language of quantum mechanics. Our entire sensory experience, the very foundation of our interaction with the physical world, is built upon an elegant and profound illusion. What our classical intuition screams is contact, the firm, undeniable meeting of two objects, is, at the scale where reality is truly forged, something else entirely. It is a silent, invisible standoff, a powerful repulsion enacted across an infinitesimal gulf of empty space. What feels like solidity is, in fact, an invisible quantum force field that prevents the atoms of your body from ever truly merging with the atoms of the world around you. To understand this, we must discard our human-scale perspective and journey downward into the subatomic realm. Imagine your hand resting on a wooden table. To your senses, it is a simple, unified event, two objects present and in contact. But let's zoom in. First, past the skin, past the cells, down to the molecules. Already, the image of a solid, continuous surface begins to fray. We see a lattice of atoms vibrating with thermal energy, a complex and mostly empty architecture. Now, let's push further into a single one of those atoms. The old planetary models you might have seen in textbooks, with electrons orbiting a nucleus like tiny moons, are a useful but deeply misleading simplification. The reality is far stranger. At the center of the atom sits a fantastically dense nucleus containing its protons and neutrons. If this nucleus were the size of a marble placed at the center of a massive sports stadium, the atom's electrons wouldn't be other marbles zipping around the stands. Instead, they would be everywhere and nowhere at once, existing as a hazy, probabilistic cloud, a wave of potential that fills the entire volume of the stadium. The atom, the fundamental building block of you and the table, is almost entirely empty space. So, when the atoms of your hand approach the atoms of the table, what is actually happening? The first and most intuitive answer lies in one of the four fundamental forces of nature, electromagnetism. The electron clouds that define the outer boundaries of your atoms are negatively charged. Likewise, the electron clouds of the table's atoms are also negatively charged. And as high school physics teaches us, like charges repel. As the two swarms of probabilistic clouds get closer, this electromagnetic repulsion skyrockets. This force is what your nerves interpret as the sensation of touch and pressure. It's an electrical force pushing back, creating the illusion of a solid barrier. This is a perfectly valid piece of the puzzle, and for many explanations, it's where the story ends. But it leaves a deeper, more unsettling question unanswered. Why is this repulsion so absolute? Why don't these probabilistic clouds, these ghosts of potential, simply interpenetrate and merge under pressure? If atoms are mostly empty space, governed by fuzzy waves of probability, why can't you just phase your hand through the table? The electromagnetic force explains the push, but it doesn't fully explain the unyielding, non-negotiable of matter. It doesn't explain why atoms maintain their integrity, their distinct volumes, and why the very concept of solidity exists at all. To simply say electrons repel each other is to miss the true ghost in the machine. There is another law at play, a deeper and more bizarre quantum rule that operates beneath the surface of electromagnetism. It is a law not of forces, but of identity, a cosmic decree that forbids the very act of sharing space in a fundamental way. This principle is the true architect of the physical world, the silent guardian that enforces the separation between you and everything else. It is the reason the universe has form and substance, rather than being a featureless soup of collapsed matter. So, if simple repulsion isn't the whole story, what is this profound unseen barrier that truly defines our interaction with the universe? From that startling revelation of non-contact, the universe's most fundamental and perhaps least appreciated law, the Pauli Exclusion Principle. This is the true ghost force we were searching for, and it is the bedrock upon which all of chemistry, biology, and the very structure of matter is built. Proposed in 1925 by the brilliant and famously critical Austrian physicist Wolfgang Pauli, it wasn't born from a grand theory of everything, but from a desperate attempt to make sense of the strange behavior of electrons and atoms, as revealed by the light they emitted. Classical physics had completely failed, and a new, radical set of rules was needed. Pauli provided one of the most crucial. In its simplest form, the principle states that no two identical fermions can occupy the same quantum state simultaneously. This sentence, though seemingly abstract, is one of the most powerful in all of physics. It is the universe's ultimate rule of personal space. To unpack this, we must first understand its terms. A fermion is a category of particle that includes all the building blocks of matter, the electrons, protons, and neutrons. They are distinct from bosons, which are typically force-carrying particles like photons. The crucial difference is that bosons love to clump together in the same state. It's how lasers and superfluids work. Fermions, on the other hand, are cosmic individualists. They are fundamentally antisocial. The second term, quantum state, is essentially an electron's unique address within an atom. This address is defined by a set of 4 quantum numbers, which specify its energy level, the shape of its orbital, its orientation in space, and, most critically for Pauli, its intrinsic angular momentum, or spin. An electron can be spin up or spin down. The exclusion principle, therefore, dictates that within a single atom, you can have at most 2 electrons in any given orbital, one spin up and one spin down. Every other electron must find its own unique orbital at a higher energy level. They are forbidden from piling up on top of each other. They are, like tiny quantum guardians, each defending its own unique quantum territory. Now let's connect this back to your hand on the table. When the atoms from your hand get infinitesimally close to the atoms of the table, their electron clouds begin to overlap. The electrons in your atoms are now trying to occupy quantum states that are already taken by the electrons in the table. But the Pauli exclusion principle forbids this. It's like a cosmic game of musical chairs, where every single chair is already occupied. For the electrons of your hand to squeeze into the space occupied by the table's electrons, they would be forced to jump into much higher unoccupied energy levels. The amount of energy required to do this is colossal, manifesting as an immense repulsive pressure known as electron degeneracy pressure. This is the true source of solidity. It's not a force in the classical sense like electromagnetism. It's a consequence of the very fabric of quantum mechanics, a structural inevitability. The universe would rather create a force of immense power than allow 2 electrons to share the same quantum address. This is why you don't fall through the floor. The floor isn't solid because it's full of stuff. It's solid because its electrons and yours are fiercely defending their quantum identities. The consequences of this single, elegant principle are staggering, sculpting our universe from the atomic to the cosmic scale. It is the sole reason that chemistry exists. By forcing electrons into a tiered structure of shells and subshells, the exclusion principle creates the periodic table. It dictates which atoms will bond, how they will bond, and the infinite variety of molecules that can form, from water to DNA. Without it, all electrons in every atom would collapse into the lowest possible energy state, and the universe would be a chemically inert, featureless sludge. But its power extends far beyond the tabletop. Look to the stars. When a star like our Sun exhausts its nuclear fuel, its own gravity begins to crush it inwards. The star collapses, becoming smaller and hotter until the atoms are squeezed so tightly that the electron degeneracy pressure, our ghost force, kicks in. This quantum pressure single-handedly halts the gravitational collapse, creating an incredibly dense, stable stellar remnant known as a white dwarf star. A mass comparable to our Sun squeezed into a volume the size of the Earth, held up against the infinite crush of gravity not by fusion, but by the Pauli Exclusion Principle. And when gravity is even more extreme, in the collapse of a much more massive star, even this pressure can be overcome. Electrons and protons are forced to merge, creating neutrons. The star collapses further until it is halted by a new wall of repulsion, neutron degeneracy pressure. Neutrons, also being fermions, obey the same rule. The result is a neutron star, a city-sized object with more mass than our Sun, so dense that a single teaspoon of its material would outweigh a mountain. The Pauli Exclusion Principle is the silent architect of our world, the invisible law that gives matter its form, its stability, and its very substance. It is the reason you exist as a distinct, solid object, forever separate yet intricately connected to the cosmic whole.